of exponentials, we're looking at exponential modelling. Okay, obviously really important at the moment with what's happening, and this is a proper real life scenario now, with all scientists using exponential modelling to try and predict what's happening with the coronavirus. So there's two key features first of why we use exponential functions to model them, especially for population growth and decay and things like that. Okay, first of all, increases by 1x 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 increases by 1. Okay, so what we're saying is it gets bigger and bigger and bigger depending on how big your power is. Okay, so with population growth, we typically have a fixed percentage increase each year. So if we think to compound interest, so for banks and things like that. Okay, so the growth is 10%. So we would use 1.1, and then we will multiply by how many years, and that will show that that 10% increase each time. Okay. The other thing, and the most important thing, and this is why we use it especially for things like tracking diseases and things like that, is the rate of increase is proportional to the size of the population at that time. So a 10% increase, so by increasing by 1.1 to the power of whatever, okay, is all relevant to what the initial population is. So, for example, if you compared us to America, America has a much bigger population. So when we do a 10% increase, okay, obviously the increase itself is going to be so much more because you're doing 10% of a bigger number. Okay, just want to have a quick look at some of the sort of questions you'll be asked. These aren't too bad at all, guys. Okay, they're not too difficult. So, first of all, suppose population P in the Republic of Dave is modelled by P equals 100e to the 3t, where t is the number of years since the Republic was established. What is the initial population? Well, the initial population, you will always be asked about initial parts or starting values. That is always going to be when t equals 0, or whatever variable they've used for the power is. Okay, because when t equals 0, e to the 3t is obviously going to equal 1. Because we'll have e to the 0. So we're left with 100 times by 1. So we will have an initial population of 100. Okay, really important. Whenever they ask for initial population, initial value, starting value, whatever that is, you make your power equal to 0, whatever that variable is. Okay, what is the initial rate of population growth? Now, this straight away talks about rate of change. Now, there is one thing that should come into your minds now whenever someone asks you about rate of change. Okay, rate of change means gradient. Gradient means differentiation. Okay, so whenever you are asked about a rate of change, the first thing that should come into your mind is differentiation, which means I've got to differentiate my function. Now, we looked at the differentials of e, okay, last week. So my differential is going to be in the form of dp dt, because I'm differentiating p in terms of t. Okay, e to the 3t differentiates to 3e to the 3t, but obviously I've got to multiply my 100 and my 3 together, so I'll have 300 e to the 3t. Okay, and the initial, because obviously that's going to be important, initial means we'll have t equaling 0. So when t equals 0, my initial rate is 300. Okay, so 300 people per year. Okay, finally, sketch the function. Well, first of all, you need to think about, is it a growth or a decay? Seeing as my rate of change is 300, it means it's got to be a growth. Okay, and there's always going to be one important thing to remember when we do these, and that's going to be our starting value. So when I do my exponential growth, I've just got to remember I put on my starting value of 100. Okay, really nice and simple, guys. It's just a bit of combination of what we've done over the last week or so, but all into a real life problem. Okay, right. Can you pause the video and have a quick go at the question that is now on your screen, and then we shall go through it afterwards. Okay, guys, so this one's taken straight from the textbook. Okay, very, very typical sort of question, typical sort of layout of what you're probably going to get. Okay, so the density of a pesticide in a given section of field can be modelled by the equation P equals 160e to the minus 0.006t, where t is the time in days since the pesticide was first applied. Okay, so use the model to estimate the density of the pesticides after 15 days. Well, as soon as you're asked to do that, all you're going to do is substitute in a value, and your value is going to be t equaling 15. Substitute it into there, use your calculators, and we should get P come out as 146.2. 146.2 milligrams per meter squared. Okay. Part B. Interpret the meaning of 160. So the 160 sits in front of my exponential part of my function. Whatever number that is in front of it, okay, if I think about what value of t I'm going to have, well, when I have t equaling 0, I'm just going to be left with my 160. That means that 160 must be the initial value. Now, be really careful with this, because sometimes you might have a slightly different power in here, and you've got to be really, really careful. Okay, but 160 will be the initial value, so it's the initial density of the pesticide. Okay, pesticide. Okay, part C. Show that dp dt equals kp, where k is a constant. Okay, so I'm asked to do my differential. Okay, so you have to do the same thing as the last question, it's just in a slightly different model. Okay, so it's telling you you've got to differentiate it now. So I've got p is 160 e to the minus 0.006t. So remember, e to the kt becomes ke to the kt. So I'm ended up with 160 times by 0.006 e to the negative 0.006t. And that's going to come out as minus 0.96 e to the minus 0.06t. Okay. Make sure we are nice and happy with these differentials of exponential functions, because they will come in really, really handy later on. Okay, right. Part D. Interpret the significance of the sign of your answer. Well, I've got a negative value here, which means whatever value comes out as t, whatever number I get, whatever this part here comes out as, okay, I'm going to get a negative number. That means it's got to be decreasing. My rate of change, okay, is decreasing, which must mean my density of pesticide is decreasing. Okay, so this is a exponential decay rather than a growth. Okay, so it's going down each time. So when finally we have to sketch our function, our key value, which is going to be our 160, because our starting value, but is now a decreasing exponential. All they are after in terms of a sketch in this case, guys, is your starting value, so your y-intercept, and then the shape of your graph. None of this should be too challenging, guys. Okay, check back on to show my homework, see which questions I want you to do from exercise 14C. If you have any problems, please email me.